Hello, Chem 1B. This is Chapter 18, Video Lecture 9, or Lecture Video 9. And we're going to be talking about, finally, how does an equilibrium constant change with temperature? And we can actually determine that using some of the equations we've already talked about in previous lecture videos. So, for instance, we know that it varies with temperature. This is actually due to the entropy change for the surroundings depending on temperature of our reaction. Now, we know from the previous lecture that delta G naught is equal to negative RT ln of KEQ, or our equilibrium constant. Now, we also know another equation for delta G. We know that delta G is equal to delta H minus T delta S. Now, I can put these two together, right? If I bring them together, I can get this equation, right? Where RT times ln of K is equal to negative delta H plus T delta S. And if I rearrange a little bit more, I finally get this equation. Now, this equation allows us to calculate the equilibrium constant for a reaction at any temperature as long as we know both delta H and delta S for the reaction. It's a very useful equation. So, there we go, better. By comparing two temperatures, so this is kind of the one temperature equation, we can actually divide it by itself under two different temperatures, and we can get another equation. The two temperature version looks like this. It kind of looks like the Arrhenius equation we learned about in chapter 13, except the really only difference is this is EA for Arrhenius, and these are rate constants. Otherwise, it's pretty much the same equation. But in this case, we're using equilibrium constants, and so these are KEQs. Our equilibrium constants, here's our delta H of the reaction, right? And these are our temperatures 1 and 2. And R is 8.314. Cool. Now, we can use this equation now to solve for KQ at a different temperature if we know it at one temperature, or if we know both the delta H of the reaction and the delta S of the reaction, we can solve for what our equilibrium constant is at any temperature we want, which is super useful. All right, so let's do an example problem. So in this equation, in this problem, we can see that we want to find out what the equilibrium constant is at 50 degrees Celsius when we know the delta H and the delta S. So this problem relies mainly on that delta H of our reaction, negative of that, over RT, plus delta S of our reaction over R is equal to the natural log of KEQ. And so we know T, albeit in Celsius, we need to change that to Kelvin. We know delta H in kilojoules per mole, and we know delta S in joules Kelvin per mole, or joules per mole per Kelvin. So in this problem, what we need to do is kind of just plug in and solve. We know we want to solve for our KEQ here, and we know that negative, again, we're in kilojoules here, R is usually given as 8.314 joules moles Kelvin. So one of the most common mistakes is not correcting for the kilojoules joules issue. So I'm going to say this is equal to negative 45,600 joules per mole. And I'm going to divide that by 8.314 joules moles Kelvin times our temperature in Kelvin. Now we need to add 273.15 to 50 to get it in Kelvin. So that will be 323 Kelvin. I'm going to add 234 joules over moles Kelvin and divide that by 8.314 joules moles Kelvin. Now if we look at this, the units are all going to cancel out. And this is important because the natural log of a value has to be unitless. So we shouldn't have units on the right side. At this point, we can just kind of plug into our calculator and solve for what that value on the right is. So you should get approximately that natural log of KEQ is equal to 11.166 164, 165, give or take. Take the E of both sides, and we get KQ is equal to about 7.06 times 10 to the 5. Or sorry, to the 4th power. And that is our answer here. Okay, so let's do one more problem, and this will be the last slide or problem we do for chapter 18. So in this problem we have, what is the equilibrium constant at 60 degrees Celsius if we know we have a delta H of 65.2 kilojoules per mole at 45 degrees Celsius. And the equilibrium constant at that temperature is 4.34 times 10 to the negative 4. So effectively, we're going to be using our equation that we learned about, right? ln of capital K2 over capital K1 is equal to negative delta H of our reaction over R times 1 over T2 minus 1 over T1. And at this point, we have the delta H, right? We always know R. So we have those values. We have a T1 and a T2, and we have a K1. So we need to solve for K2. All right, so let's plug in some numbers. The first thing I'm going to do, though, is I'm going to change some of my values from temperatures in Celsius to temperatures in Kelvin. And so for the 60 degrees Celsius, we get 333.15, and for 45 degrees Celsius, we get 318.15 Kelvin. Now, I also need to change my delta H or my R value into the correct units, right? Kilojoules, need to change that to joules if we're using R as written, or vice versa. So let's kind of fill in our whole deal here. I'm going to say this equilibrium constant here is my K1. So K2 is what I'm trying to solve for. So I know 4.34 times 10 to the negative 4 goes here in the denominator. And this is going to be equal to negative 65,200 joules per mole all over 8.314. And then that's 1 over the 60 degrees because that's what we're trying to find it at, right? So 1 over 333.15 minus 1 over 318.15. All right, so at this point, we can do some math. I'm just going to calculate everything on this side in my calculator to start off with. And what this gives me is that ln of K2 over 4.34 times 10 to the negative 4 is equal to 1.1098 give or take. And I need to get rid of that natural log on the left. So I'm going to take everything e to the power of everything on both sides. What this does is it'll cancel out the ln's here, and then we'll be left with just K2 over 4.34 times 10 to the negative 4 on the left, and whatever value e to the power of 1.10983 is on the right. So let's kind of move our stuff up here. So now I have K2, the equilibrium constant I want, over 4.34 times 10 to the negative 4 is equal to 3.0 4.34. And all I need to do now to solve for K2 is multiply both sides by 4.34 times 10 to the negative 4, which gives me 1.34 times 10 to the negative 3. And this is my equilibrium constant at this temperature. Because the delta H is positive here, I kind of had a feeling that as we increase temperature, our equilibrium constant should go up, and it did. Right? It was at 45 degrees Celsius times 10 to the negative 4, and now at 60 degrees Celsius it's times 10 to the negative 3. All right, so if you have any questions, as always, please let me know via email and or discussion sessions.